All right, so we're going to go ahead and get started here this morning. Good day, everyone, and a pleasure to have you here today. My name is Gabe Gums. I am with Myota. I'm one of Akamai's ISV partners. By way of background, Myota is a data security organization. We've been around for coming up on a decade. Myself, I am actually a hacker by trade. So I've been an ethical hacker for the better part of about 26 years. I am most adept at breaking things. So I have a little bit of knowledge on how you might survive things getting broken. And essentially what Myota delivers is a platform that is designed to survive those kinds of breakages. From our perspective, there's really not much difference between when things break and when they go wrong. You know, if I asked you the question, what does ransomware and the recent outages have in common? The answer is essentially the same. They're availability problems. In the world I traditionally come from in security, we talk a lot about confidentiality, integrity, and availability. Those are the three core tenets of security. Without all three, one does not have security. That availability part gets a little overlooked and oftentimes left to you to solve for on your own. I mean, as we've seen in recent events, you are largely beholden to the architectural designs that either you created on your own or your service provider created for you. And so what we look at it and what we ask is, again, the difference between the two. In a cloud outage, your infrastructure becomes unavailable. Your infrastructure becomes unavailable. You can't access any services. I probably don't have to tell you guys how difficult it is once TikTok goes down. Actually, I couldn't tell you at all. I don't use any social media. I did mention I hack for a living, so you should stay off of it yourself. But ransomware, not terribly different. What happens? Your data equally becomes unavailable. In both scenarios, what you're actually experiencing is an availability problem. You're experiencing an exploitation, if you would, of single points of failure. And when I use that word exploitation, I don't necessarily mean it in just a negative connotation. S happens. Sometimes things simply happens. And so what we do is, and what I'll show you here today, is an architectural pattern that addresses and eliminates those single points of failure. And I want to be clear about that. This is very much an architectural design pattern that is enabled by our technology. It is not simply magic software under the hood, if you would. So in traditional, quote, zero trust environments, you're largely focused on the identity and the network layer. Again, Myota introduces zero trust at the data layer. And when we talk about zero trust, we talk about it through all the tenets that the actual NIST protocol talks about, starting first and foremost with you should assume compromise. You should assume that the environment itself is compromised in some way. From an infrastructure perspective, that compromise might literally just mean a region is down. From a security perspective, it might mean that accounts were compromised. Either way, you need to be able to withstand and be resilient and recover from those events. And the gap that still exists is in a lot of that trust still largely rests with the provider itself. We don't, or I should say didn't, have the ability to extend that requirement to ourselves. So what does zero trust look like at the data layer? Again, I'm going to use those same words just to reflect the trust conversation. Well, A, you shouldn't trust a single location for all of your information. All of the things should be in all one place at the same time. Fun fact, IBM invented the first backup drive before the first hard drive. Most of you probably don't even remember that. That's okay. I wasn't born when that happened, but it's true. Like, we have known for longer than we have remembered that you should do things like keep multiple copies of your data in multiple locations. It's one of the reasons why we build highly available infrastructure using platforms like Kubernetes to begin with. And so when you start implementing zero trust at the data layer, you don't have to trust any singular location of where that data might be. You don't even have to trust any singular provider of where you're hosting that data. When you distribute it across regions and or providers, you start to build in a level of resiliency that allows you to, again, withstand outages and or attacks. So what do you unlock when that happens? You unlock three things, three very important things. You unlock portability, recoverability, and survivability. So portability, pretty important. First and foremost, as the cloud goes today, it's fairly easy to get locked into the cloud. One of the great things about Akamai as a provider is they have a very portability first approach to how they approach the cloud, making it such that you can build on their platform and, well, move that infrastructure anywhere. When you leverage this architectural pattern that I'm describing, you'll see how those two things come together. Recoverability. You have to be able to recover from any of those events. It is not enough to simply survive an outage, whether it's an IT one or a cyber attack. You have to pick right back up to before that event happened. That's usually where the real work begins. That's usually the messiest part. Once the internet came back live a few weeks ago for most folks, like we just went back about our days. For most of the people in this room who were actually dealing with the technology kind of fallout from that, there's still a lot of work to go to recover from those outages. And again, surviving those things, survivability might literally just mean, it might for some organizations mean the difference between going out of business or not. Certainly when it pertains to the cybersecurity side of things, we've seen far too many organizations be hampered by their ability to continuously grow post-incident. And the same thing from an IT perspective, losing that kind of revenue when your services are down. You don't just instantly regain it the second they come back up. You've got to be able to survive those things, both from a technology perspective and a business perspective. So what does Myota's technology actually bring to this? How do we do this? And I promise I won't bore with just slides. We've got a couple of minutes. I want to show it live in action as well, too. So what we have is this platform that we call Shard and Spread. Shard and Spread is a patented technology that allows us to take the data, make it completely useless to attackers. So again, we're going to withstand those types of outages, and then distribute it across any type of back-end infrastructure, allowing for that infrastructure to be completely destroyed and still be able to survive it. Under the hood, what's happening is a series of things. It first goes through a quantum resilient protection mechanism. There's 2 security primitives under the hood. I won't get super technical, but if anyone is actually interested in more details, happy to explore those. But know the following: it's quantum resilient. You could blink your eyes, you could have a quantum computer tomorrow. You cannot reconstruct that data. The second is taking that data and breaking it into pieces. So sharding also has been around for quite some time. That's not exactly new from a technology perspective, but how we put it together in this architectural pattern is indeed different. And so we take that data, we shard it, and then we geographically disperse it to different locations. By default in design, we spread that across multiple different Akamai regions, but you can do that across, again, multiple providers, such that if something were to go down in one region, you just keep humming. And this is not a failover scenario, right? Like, this isn't traditional HA in the sense that, oh, something went down and now it's going to flip back over. This is basic routing. This is just a straight up basic routing exercise. So when you have the Myota solution sitting here on an LKE stack within the Akamai environment, you're simply just going to point your application to that standard S3 API. So one of the beauties of the Myota platform is you don't really have to do anything uniquely different. You're reporting to URI over here with the access key and a token, then you're going to just point to a URI over here with a different access key and token. That's it. Everything else happens as a byproduct of what these controllers are doing. This mesh setup between where it is sending data, and in this scenario, I have it set up such that we have 2 nodes over in AWS and 2 in Akamai. If you haven't picked up on it, my sharding methodology is using the threshold reconstruction setup. So although I've distributed 4 shards, I only need 2 for recovery. It looks and feels a little like RAID and erasure coding in that sense. You can think of it that way, but we're simply building on those concepts. So let's do this live and actually see what happens, see if the demo holds up. So first, we're going to simulate an actual outage. If this were a week ago, I wouldn't have to simulate this. We could just do this live if it was a week ago, but it's not. So I'll go ahead and simulate that first, and then we're going to simulate this happening. Fun fact: something similar happened to a large data set in Brazil about 1.5 years ago. They were hit with a flood, and their primary data center went down. And about 12 hours after that flood, there were already some attackers dwelling inside, and they thought, what a perfect time for me to announce my presence. So they went ahead and ransomed the rest of the environment. So this is one of the 2 large data centers in Brazil. And so as they're doing that, they go down, and as they're down, they then get hit with ransomware. So let's do this in real time. So here, what I've done is we've set up essentially an arbitrary application. This is the Myota controller, and it is connected to, as you can see down here, 4 different backend storage nodes. So that architectural diagram I was showing a second ago with Cortex and the Kubernetes kind of pointing to these 4 different locations. And so we've got 2 over here in Akamai. We've got 2 sitting over here in AWS. And what we're going to do is we are going to first, I will upload another file here. There we go. All right, it's going to go through that Myota shard and spread process. So again, that quantum resilient encryption process occurs, breaks it into these unusable shards. So even if, for example, you were to break into this back end, there's nothing here that's usable. You can't reconstruct this data at all, like literally, impossible to do so. But from a IT perspective, from just a pure, I said we were going to simulate an outage first. Let's go ahead and let's take down some of this infrastructure. So I'll take down that node and that node, and we will fail those 2 nodes down. So now we have an outage. It's last Thursday, AWS is offline. But with the Myota platform, doesn't matter. When you're running the Myota platform in an Akamai environment, I still have the ability to access all of my data. Now, why is this happening? The answer is because, apologies for the slowness, it's going through the mess that is all of this internet air right now. The answer is because it's that threshold recovery. Never once did we centralize any of the data in any single location or any of the controls around it, so I can always pull that. By the way, this is flexible. I have it in a 4/2 configuration, but if you said I actually need greater resiliency or I want to have more diversity, you could have that be 6 nodes, 90 nodes. It's theoretically infinite. We've never tested up to infinity, but we've tested at some pretty high exabyte scale and know that that will go pretty high before anything happens. So that file was downloaded. Alrighty. And so with that, we're having a bad day. Half of our infrastructure is down, but it's not that big a deal. We'll let the boys and the girls in the back work on that. But as I mentioned, real world scenario happened to those folks in Brazil. Half my infrastructure is down. Attackers take this opportunity to go ahead and execute something nefarious at the same time. So what else is actually happening under the hood here? Well, there's a few things happening. I'm not simply breaking data up and writing it to these different locations. There's a README file that I'm certain if I open that README file, it's going to have some gorgeous instructions as to where I can wire all of my worldly goods, firstborn, etc., etc. But we're going to tell them to pound sand in a moment. What's happening under the hood is a few more things. I talk about shards in the abstract, but we break your data up into multiple different things. There are content shards, just has all of your content. There are metadata shards that essentially tracks, well, the recipe to how to put the things back together. And this has a couple of benefits. It is also not centralized. So there's no one place for an attacker like me to go take it offline or any one place where it might just say go offline. But we're also doing the same thing with keys. So there's no key management required. It's built into the data itself, meaning, again, there's no key infrastructure to be compromised that can go down or, again, simply just attack. So I'm in this scenario. Data has been compromised, but I'm using a write-forward method to those metadata shards. There's a level of immutability that's built in by default to this type of HA object storage. In traditional object storage, for you to achieve immutability, what do you need to do? You've got to go press that little immutability button. You got to turn on version controlling. Voila, you have it. You have a couple of challenges with that. As an attacker, I have more than a few ways around that. Some of my favorite particular ways is just poison the data. Like if I can't get to it, I'll just shit can it on the way to where it's going and make sure that when you go to retrieve it, it's not terribly useful to you. But there are a number of other ways around that. So not this last DEF CON, but the one before that. If you ever visit some of the hacker conferences, we took a bunch of these backup technologies and other storage technologies, and we put them in a room and we attempted to see how well their immutability held up. And many of them were rightfully so built on top of Linux systems. So immutability in those environments simply meant change attribute, plus I, minus I. That's awesome right up until I escalate privileges and it's just a simple matter of removing that control. So what's actually happening here is anytime there's a CRUD event, every create, read, update, delete event, that gets written to one of my metadata shards. Those same immutable shards that cannot be destroyed, but that also live in multiple places, such that if the infrastructure itself goes offline, I still have access to them. What that is doing is it is essentially keeping a DVR-style recovery system so I can move back in time to any point before something happens. So in this case, I'm just going to slide back. I'll just go 5 minutes ago to before that ransomware made my life difficult. And I'm right back to where I started from. And this isn't recovery. I don't have to go and pull a file back and rehydrate it. It's a pointer. Essentially, I'm just moving a pointer from this point in time to that point in time. And this immutable log, you can think of it similar to how blockchain writes to an immutable log. But know that this is far from blockchain technology. I only use that analogy if you're familiar with it. I would never implement blockchain. And well, I'll tell you what, I actually don't know how to implement it in any meaningful commercial way. If I figure it out, though, you'll see me back here telling you all about it. But the concept under the hood is essentially the same. I'm writing to an immutable log, a shard that allows me to just then create this pointer. I'm also not creating full copies of the data throughout this process. So I'm not imploding the storage costs associated with this type of activity. In order to get that same kind of data resilience, you'd have to end up usually with about 300% times the amount of data. In this scenario, that's not going to happen. So all I simply did was I rolled back. I went back a few minutes. I'll go back a few minutes further. Also useful, I can go back forward in time. So again, as an attacker, but these days I spend most of my time on the defending side of the world, very useful from a recovery perspective, very useful from a forensics perspective. I can move forward and backwards and leverage this environment now as an isolated recovery environment to see what happened. But most importantly, you'll still notice my data is still accessible. Nothing has stopped that from happening. And when these nodes come back online, again, the system simply continues to work as it did before. So what you were seeing under the hood was this architectural infrastructure coming to life. You saw us take down these two nodes, and essentially it was just a different routing that allowed for us to still get to our data in the Akamai Cloud. The same thing happens if the compute environment goes down. These are just running on LKEs, so they're always highly available as well. And then on the front side of things, from an application perspective, what do you have to do to make sure that your application can leverage this technology? Well, if I can find my mouse again, there we go. It's a simple code change. Again, you're just pointing from one URI to another. So this is what it would have looked like before you implemented the Myota secure storage environment. And all you're really replacing here is you're adding the endpoint URL and you're swapping out a different access key and token. So when you have a cloud-ready, cloud-first application, in order to take advantage of everything I just showed you, this is essentially it. That's your setup time. That's it. You need to have that application repoint to it's a fully S3 compatible interface. Kind of give you a bigger look at what that looks like when it's running in this multi-region HA environment across the Akamai Cloud. This is essentially exactly what it looks like. So we deliver this both as a service, but customers can run this within their own tenants as well. And again, it's as simple as spinning up an LKE and connecting it directly to your object storage. These are all located across the Akamai Cloud. But if you wanted to, these can and do connect. We have customers that run it in hybrid mode. So where you have large data sets that need to be accessible in the cloud, say for analytic workloads, because you are, like everyone else, trying to do something AI these days, but you have a lot of that data equally locked away on premises where your developers are doing things with it. This allows you to extend that fabric with one, and this is really important, you get one namespace. You create one single namespace across this storage environment. So I can do some cool stuff that you can't do literally anywhere else. For example, you can replicate data across regions within the same account. You can't replicate them across different accounts in different regions on any cloud provider platform. Why might that be useful? Well, what happens when I do an account takeover? That's why that might be useful. You might want to literally separate, again, from a zero trust perspective, the control you have over even just the granularity of this infrastructure. But doing that with today's design patterns just aren't possible. You cannot spread that data across accounts and regions. There is no way that I know of to do so. Happy to hear someone else bring that to me. And if you do, I'll have my lawyers talk to you because my patents definitely would be. No, I'm kidding. I'm not that litigious. I told you I'm a hacker. I'm just going to show up in your bedroom later tonight. Uh, so the storage efficacy, the math behind all of this. So essentially what we're doing again is we're not replicating data. This is not a full replication system that just found a faster way to replicate data and then rehydrate it and pull it back. That replication adds a lot of infrastructure costs. It adds, quite frankly, even more infrastructure costs when you start doing things like adding in all of the additional controls you need around it. We are just short of having that much infrastructure while providing almost infinite resilience in comparison. So why would you use this? Well, ideally, if you're working with large amounts of data, and by large, I mean, once you start getting into multi-terabyte ranges and petabyte ranges, much less exabyte ranges, that data is going to require that level of resilience. And again, when we talk about resilience, we don't talk just about IT resilience. We talk about IT resilience and cyber resilience. They are one and the same. They both suffer from the same architectural limitations. And at the end of the day, you suffer from the same problems when affected. It's an availability problem. So if you are needing or requiring that type of survivability while also managing costs, and I challenge you to show me one person in this room who hasn't been asked to look at costs, then something like this might be worth exploring. All right, I think I managed to get through that in time, maybe less time, more time, I'm not sure. I was trying to push past, so I didn't want to eat up too much time in slide and actually show you guys live inside the demo environment, but I will be here and happy to bust out the laptop and show it a bit more, answer any questions that anyone might have. Thanks again. I appreciate folks coming out, and my name's Gabe Gums.